All right, how's it going, everybody? I am here on Monday, April 26th, making this video. Today, we're going to talk about sections 11.4 and 11.5. But more importantly, we should talk like our broader like wrap up to the class discussion right now. We still want to get all the way through 11.10 to wrap up this class discussion of Taylor and Maclaurin series. I've already written our homework assignment for section 11.10. We're going to make it there, I promise. We still obviously have a few sections to get through on the way there. The good news is that most of these sections are very closely related. Most of them are pretty short. One of them is a summary section. So it's going to be pretty reasonable for us to sort of, I don't know. This is going to seem like a lot and like it's difficult. I'm hoping that you find these all to be more like interesting algebraic proof puzzles rather than a mountain of work. So what we still have coming up here is that this week, in week 14, we're going to hit today. We're going to hit the comparison test. That one's going to be relatively easy because we've already seen two other comparison tests this semester, one for integrals, one for sequences. Today we're getting the comparison test for series. We're going to look at alternating series. What happens when series have terms that alternate positive and negative back and forth? We're going to get a very convenient test associated with alternate series. In our next video, we're going to look at 11.6 and 11.7. You should see that 11.7 is really strategy for testing series, which really means I'm just going to sort of fold in the broader concepts about strategy for testing series into our 11.6 discussion. And the bottom line is that we're going to do like, we're going to judge the convergence or divergence of like 20 or 25 different series in this video and in the next video between these two four sections right here. So this video. This is our next video. Then we've got our stuff going on next week there. Next week, we want to introduce our power series and our series representations as functions. And then finally, our most important conclusion topic here is Taylor series, or Maclaurin series is the special case of Taylor series that's centered at zero. So Taylor series, really, really, really important idea that we that's going to be one of the key thing that you're expected to know for any class in the future that care. If they say, hey, did you take Calc 2? There's about a 50% chance the reason they're asking you that is to ask, do you know what Taylor series are? So that's kind of like a key thing that we got to get through at the end here. And then that next week is our last regular content week. Week 16, we'll have our final exam. It'll be a lot like the midterm. I'll make it available on Canvas. You guys are going to do it and submit it in Canvas. And yeah, I think it'll go pretty similar to how our midterm went right there. So we'll talk a little bit more about that next week here. So in a sense, kind of feels like a lot. We're definitely covering 7 sections in the next 2 weeks here, but a lot of these, I really like to think of like 5 of the sections in chapter 11 are really just one long section, which you should say to yourself, well, doesn't that just mean it should be broken down into multiple sections? And yeah, that's why the book does that. But again, these are all really closely related to each other. All of the algebraic manipulation associated with all of them is relatively similar. A lot of what this ultimately boils down to is, can you be smart about your strategy once you've seen all of the different tests for convergence and divergence that we have? And so that's, going to be a little bit more of the component of next video. But again, I think in this video, we're doing something like 13 examples here. We're going to see a lot of the things that can happen. That's going to hopefully poke you in the direction of that your intuition should be encouraging you to look. And so let's remind ourselves again that what we're starting with here today is something you have already seen more than once. And there's nothing really directly new except for the realm to which we're applying it. Comparison tests in general are useful for scenarios where we cannot directly determine a desired piece of information associated with a sequence, series, or integral, but where the terms of interest, like the integrand or the individual terms of the sequence or series, are closely related to a more well-known sequence, series, or integral to which we can compare. We've already seen the comparison tests for convergence of integrals and sequences. The comparison test for series is essentially the same. So our comparison test states, suppose that the series with terms of the form a sub n and terms of the form b sub n are both series that have positive terms. This is like your number one restriction. The only thing you got to watch out for with the comparison test, they have to be all positive, is this. If the b series does converge, and if all of the terms in the a series are smaller than their partner term in the B series, then the A series is also going to have to converge because it was completely below the B series, and the B series did converge. So we're even smaller than a convergent series converges. right? So if we're smaller than a convergent series, then we converge also. The opposite statement says if our series B sub n diverges, if it's so big it tends off towards infinity, and if all of our terms in the A sub n sequence are bigger than the terms in the B sub n sequence that diverge to positive infinity, then it should be the case that the A sub n sequence or series has to also diverge because we were larger than a divergent series. Larger than divergent is going to tell us that we're going to diverge, right? We're either above a divergent series or we're below a convergent series. We can say that therefore we have that same behavior. And remember, and I've asked you questions about this, I think there was even something on the midterm about that with the integral comparison out there. Remember that if we are smaller than a divergent series, we don't know what to say. Are we smaller enough that we converged? We don't know. If we are larger than a convergent series, then what can we say? We don't know because we don't know if we're larger enough that we've gotten infinitely large or if we're just 3 times as big or something that wouldn't matter in a convergent case. Right? So the important thing about the comparison test is that you are responsible for judging what would be a good series to compare against. What that means to me is that if you don't know any series that converge or diverge, then you can't use the comparison test. So it matters that we know our base cases here. Ultimately, to me, what this boils down to is this says, do you know about the harmonic series? Do you know about P series? Do you know about geometric series? Those are the 3 series that it's relatively easy for me to state whether or not it converges or diverges. All the other ones are hard. Pretty much everything else is hard. So those are really my core for my comparisons that I make are the harmonic series, P series, and geometric series are sort of our easy ones out there. So let's cruise on down the line here. We're going to start by looking at these 4 examples right here. We're going to see that some of them we can make meaningful comparisons, some we cannot, and then we'll actually attempt to revisit some of them at some point as well here. So our first series we want to ask about the convergence of. This is the series of natural log of n divided by n. And the first thing that I'm seeing right here is anytime I see a series that has a term divided by n, I'm thinking to myself, this is related to the harmonic series. Which we know diverges. Now, an important thing I'm going to try to do here, I'm probably going to do a bad job of this, but basically anytime I ever claim I know about the divergence or convergence of anything, I absolutely have to justify that because we are not interested in ideas or examinations. We are interested in proof. And so we should be 100% certain that we know what is true and why we know it to be true. We know the harmonic series diverges because it is a P series with P equals 1. We know that all P series will converge if their P is greater than 1. This has a power, this is n to the first power, so this is a P series with P being equal to 1. So the comparison that we can make then is that the natural log of n over n, the individual terms, our a sub n's, are clearly greater than the b sub n's associated with the 1 over n terms right there. Right? This is like my a sub n is greater than b sub n right there. And now, is this now a statement that we had made up above right here is that this needed to be true for all values of n that are positive integers. Is this always true? Well, if n is 1, that's not true because we get 0 over 1 equals 1 over 1. If n equals 2, then we're going to get 0.693 over 2, which is like 0.35 or something like that, is not bigger than 1/2. If n is 3, I think that we end up getting that this is going to be a legit comparison right here. Let's see, can I bring up my... I'd like to double check this real quick because this stuff obviously kind of matters right here. If you can't tell me if a series converges or if you can't tell me if one function is above or below another, then you can't use this test, right? So what I can do over here is I can do things like natural log of n divided by n. Okay, it wants x's. And I can look at y equals 1 over n. And what I can see right here is it looks like, oh, at E is where we do get that the R series is in fact larger than the harmonic series. So it looks like for 3 and beyond, R series of interest is greater than the harmonic series terms for n greater than or equal to 3, because 3 is the first integer value at which that is true. So it looks like this is at least a good statement for me to make up front right here for n greater than or equal to 3. Now, since we're only missing a finite number of terms for which this is not true, it should always be the case that the tail of our series is going to control the dominant behavior here, right? Because a finite number of terms can only have an influence of a finite amount of value, and we're trying to judge if something tends off towards infinity or not. That's not something you can do in a finite number of terms with an integer-based function here, right? So it seems like that is a good comparison for n being greater than or equal to 3. And since the series 1 over n diverges, and the series natural log of n over n is greater than the series 1 over n for n greater than or equal to 3, we can say that by the comparison test, we also diverge. Right? R series is known to be larger than a divergent series for all but a finite number of its terms. Therefore, it must also diverge. All right, so the comparison theory series. If you're bigger than an infinite thing, then you're also infinite. If you're smaller than a finite thing, you're also finite. That's all we're saying with the comparison test right here. So for our next one here, I'm seeing my series 1 over n plus the natural log of n. It also looks, I see this 1 over n being out here, and this is just yelling harmonic series at me. Right? I'm going to just keep on saying those justifications out there. I know why all of the convergence, divergence statements that I'm making are true. Right? So the comparison that I would want to make then is asking what's the size relationship between the terms in our series and the harmonic series that it seems like we're closely related to. Well, I've got 1 over n plus natural log of n, and I want to know, what goes in the box right here. That's my comparison factor right there. How does this compare to 1 over n? Well, what I can see is for all positive integer values of n, these terms right here are going to be smaller overall than the terms of 1 over n because we have a larger denominator right there. So, therefore, what does this tell us? Well, the harmonic series diverges. We are smaller than a divergent series. I don't know. The comparison theorem doesn't tell me anything, or the comparison test doesn't tell me anything here. We're smaller than something infinite. I don't know if we're smaller enough that we are finite, or if we are just a smaller infinity, if we're just half the size, right? Um, and this is true for n greater than or equal to 1. Uh, I should say less. Well, okay, all right, all right, all right. If n is equal to 1, they're equal to each other. So I'll say for n greater than 1 right there. So the comparison test is no info here. Our series 1 over n plus ln n is smaller than the compared divergent series. Right? You've got to be smaller than a convergent series to prove you're convergent, or larger than a divergent series to prove you're divergent. We were not one of those two cases. So this comparison does not work. Now, technically speaking, and that's kind of what I was trying to allude to with this statement in parentheses down here, when I say here, I mean with the given comparison that we have selected. It could possibly be the case that we could find a different comparison that we could make, but I don't see any like nearby obviously related functions right here. When I see n's in a denominator, I'm thinking harmonic series, and I don't have lots of other things to work with. I know that there's no series associated with natural logs that I feel 100% confident stating conclusions about, so I don't really directly see any other um, comparison that I could make right here. So I'm a little stuck on this guy, but I know that I don't personally know a good way to get to a proof of convergence or divergence based only on the comparison test. It's smaller than the harmonic series. Is it smaller enough to converge? I'm not sure. All right. Let's go ahead and take a look at our next example right here. So our next example, I'm no longer just seeing those n's in the denominator. So I'm no longer thinking harmonic series anymore. Let me get my stupid cursor out of the way. So I'm seeing 1 over 2 to the n plus square root of n. And the first thing that I'm thinking to myself is, ooh, I know about this 1 over 2 to the n. That's a geometric series that converges, right? So I'm thinking to myself right away here, this is related to 1 over 2 to the n, which I could write as 1/2 to the n, which converges. I know this converges because it is a geometric series with the r term in absolute value being less than 1, right? That's our growth factor. This says every term, every consecutive term is only half as big as the previous term there. We saw that all series where they can be constructed of this form, if the number inside of the power right here, if the base is less than 1, then we're going to converge. All right, so we've already shown that to be true in section 11.2 or something like that. So it seems like I can make a comparison because I know about the convergence of this geometric series right here. So our comparison then should be, how do they relate? 1 over 2 to the n plus root n, and I want to compare that to just 1 over 2 to the n. Well, clearly this guy over here is always going to have a larger denominator, therefore it's always smaller. And that's going to be true for all n greater than or equal to 1, right? Even when n is 1, this has one additional value in the denominator down there, and therefore it's a smaller overall fraction right here. So, by the comparison test, the series 1 over 2 to the n plus square root of n converges because it is smaller than a known convergent series. All right, so we guessed a related series by seeing that 2 to the n on the bottom that made me think of a geometric series. Based on what we've already learned about geometric series, I knew that this series converged, and therefore that immediately makes it a good candidate for me for a comparison test, just because I'm for sure that I know about it, right? It wasn't that it converged or that it diverged. It was that I was 100% certain that I knew about this function, and that I was able to make a comparison between each of the individual terms in each of the series that were out there, right? So it's always just identify a series that you for sure know about that is related to the one that's in question, and then hopefully the nature of the relationship between the two of them will allow a comparison test argument to be made here. So we converged here. Maybe I should be boxing our answers here. All right. So let's look at one more example here for this comparison test. So once again, I'm seeing this 2 to the n on the bottom, and immediately I'm thinking to myself, this is related to series 1 over 2 to the n, which we rewrite as the series 1 half to the n, which is a convergent, man. It gets tough when there's so many math symbols and all the words become 3-syllable, 4-syllable words. Things get tough. Convergent geometric series with r being less than 1. And so we make our comparison. In this case here, I'm trying to compare the terms of our series in question to the comparison series of the form 1 over 2 to the n. It is very obvious by inspection that the terms here have a larger numerator and therefore a larger overall value here. But our issue is that our series in question is larger than a convergent series. So therefore, our comparison test is going to be inconclusive here. And I'll say it properly this time. No info with this comparison. But not like I know what other comparison I'd make, but so we're larger than a convergent series. Are we larger enough that we diverged or not? We don't know. That's the entire point right here. So sometimes you see things and you're like, oh man, it's going to be perfect for the comparison test because it totally looks like this one that I know, but it sort of sets up the wrong nature of the relationship with the comparison here. And that's kind of a bummer, right? Um, so sometimes I see things and I'm like, easy comparison test. Oh, wait, it goes the wrong way right there. So something I want to point out to you real quick is this. One, we only were able to fully come up with 2 out of our 4 answers. We saw 1 diverge, we saw 1 converge, we saw 2 that provided no information, 1 where we were smaller than a divergent, 1 where we were larger than a convergent. So this is really all 4 of the possible cases that could ever happen in our comparison test. But here's the thing. There are 2 of these we were left inconclusive, right? Number 2 and number 4 we were left inconclusive. We got no information from the comparison test. Does that mean that we can't prove whether they converge or diverge? Well, not necessarily. It just means that by the comparison test we cannot necessarily, and by using those comparisons we can't prove if they converge or diverge. Seems like there should still be lots of other options that might be out there, right? So the good news for us is that there is an alternate version of a comparison test. And that's what we're going to look at here. So even when a direct comparison test fails, when we say, is this series bigger than this series, or excuse me, I should say that more properly, are all of the terms in this series individually bigger or smaller than all of the terms in this comparison series here? Sometimes that just doesn't work out to have the proper nature of the relationship between the terms. However, there is an alternate comparison test called the limit comparison test that we can use to help determine convergence or divergence of series here. And it's going to do ultimately a similar thing for us. So what the limit comparison test says is that if I've got series A sub n and B sub n, they need to be series with only positive terms. So again, we keep on getting this requirement of this only positive terms business over here. That's really, it's not a difficult restriction, but it's like if you forget that, then you're going to get some incorrect results if you got negative terms in your series out there. If it is the case that we can take the ratio of the 2 terms as n goes off to infinity, and that the ratio between them is just a finite value of c, where c is a positive number. Now, c has to be positive because it's only positive terms, but we're also saying here c is not infinitely large. It converges to some number c. Then, either both of the series converge or both diverge. So, what I want to kind of let's talk about this for like 2 minutes before we go ahead and use it. Why is this? Why am I saying this is effectively doing the same thing as the regular comparison test, the direct comparison test? And here's what I'm thinking. what we're kind of trying to show when we do these tests is that the amount larger or amount smaller that some series might be is really just something like maybe like a constant multiple, right? Like I'm saying if I'm infinitely large and you are 3 times as big as me, then you're also infinitely large, right? Those are gonna be the same. However, if I'm a finite value like 40 and you're 3 times larger than me, you're also a finite value. That's sort of like saying to me, multiplying a number by a constant, one like a single multiplication by a constant, is never ever going to be enough to change whether or not you are a divergent series, right? Or whether your value is infinitely large or not. A single multiplication, right? Well, that single multiplication factor is exactly the c. C is the ratio of a sub n over b sub n right here. So this is saying if we take the limit of the general form of the term a sub n over b sub n, that ratio right here, we get c, then what that means is that in the long run, once n gets infinitely large, these terms only differ from each other by a constant multiple from one another, meaning it's saying that in the long run, we can think about the series a sub n as being approximately equal to c times the series b sub n. And therefore, if one of them converges, the other converges, and if one diverges, the other diverges. So c is like our approximate multiplication factor between the two series terms eventually out there. Limit as n goes to infinity, right? And so again, this is really just saying if these two series are approximately just a constant multiple of one another, then if one converges, the other converges. If one diverges, the other diverges. So this limit comparison test says their convergence will match. It does or it doesn't for both of them if we get this kind of thing to be true. Now, the thing that we got to remember is that even though we're setting up a limit statement for ourselves, we are still responsible for creating one of those two series, right? This is like we were given a sub n, and we are still responsible for saying, I think a good comparison series would be the series defined by the b sub n's here. So you are still responsible for creatively determining what series is good for the comparison. But the good news is that once you've decided that, you can just throw a quick limit at the ratio of their terms, and if it comes out to be a finite positive value, they both have the same behavior. And if it tends off to infinity, then it doesn't seem like we can conclude anything, right? If we converge, then we get to make the claim that they both converge or diverge. If C tends off towards infinity, then we get no information from the limit comparison test. Let's make sure we're clear on that right there. So let's revisit the examples that we couldn't get above with the direct comparison test. All right, so here's the two that had sort of the wrong direction direct comparison above. Let's see if either of these are going to work out now with our indirect, our limit comparison test instead. So I still feel like I want to compare to 1 over n. Don't need that parenthesis. Okay, which diverges. It's a p series of p being equal to 1. So what I can do then is I'm going to go ahead and say for myself, my a sub n terms are the 1 over n plus ln of n. Oh, by the way, I want to go back real quick and say one other thing. Notice that this a sub n over b sub n doesn't tell you what series is the unknown versus which one's the known. And that makes sense because if you were to just take the reciprocal and do b sub n over a sub n, you would just be getting 1 over c, which would still have to be a positive constant that's still not tending off towards infinity. It's still not 0, so it wouldn't be getting infinitely large if you took the reciprocal, right? So like the point is it shouldn't matter what order you even do your ratio in. You're either going to get 6 or 1/6. And either way, you're going to conclude that they have the same convergence or divergence, right? So I'm just saying to you, it doesn't matter which one you call a sub n and which one you call b sub n in this scenario here. So b sub n is our comparison. That's our 1 over n stuff right there. And so what I'm going to go ahead and do is I'm going to take the limit as n goes to infinity of a sub n over b sub n. And that's going to give me 1 over n plus natural log of n, all divided by 1 over n. Oops, got my limit in there. And that's going to be the limit as n goes to infinity of n over n plus the natural log of n. And if we wanted to be formal about it, we could go ahead and factor some stuff out right here. All right, I'm thinking of this as n over n times 1 over 1 plus ln n over n, right? So those n's are going to cancel, and we're left here with the limit of 1 over 1 plus the natural log of n over n. Natural log of n grows incredibly slowly, whereas n grows, I don't know, I guess that's like our basis of comparison right there. In any event, this is going to be leaving us here with this ratio of 1 over 1 plus 0, which is in fact equal to 0, or which is in fact equal to 1. And by the limit comparison test, so by the limit comparison test, both converge or diverge. And since the series 1 over n diverges, so does the series 1 over n plus ln n. So what this is basically saying to me now, I'm just going to write it here so I can put it in a box. What this is saying to me now is I know that 1 over n plus ln n is smaller than the harmonic series, but what we just showed right here is that it is sort of trivially smaller in a sense. It didn't get smaller enough that it failed to diverge, so that it converged, right? We found that the limit of the ratio of the terms from the two series went to 1. And since it went to a positive constant, then it was the case that either both series converged or both series diverged. I know that the harmonic series diverges, therefore this must also diverge, right? That was our ultimate conclusion there. Cool. So it looks like the regular comparison test didn't get us there, but that the limit comparison test did get us there, which is pretty cool. Let's see if we can make that work out one more time right here. Our next series that we failed to get information about up above was this series root n over 2n. And I'm going to say the same thing. I still feel like I want to be comparing this guy. Damn it, cursor, get out of here. I'm not in a box. Why wouldn't I be allowed to type right now? Why does that go away? Stop going away, cursor. I need you, or I can't do this. All right, so I'm still feeling like I want to compare with the harmonic. And so let's set up kind of our basically the same statements as we did before. Our a sub n we said was our new series. Our b sub n was our comparison series. So our a sub n is root n over 2 to the n. Our b sub n was the 1 over, oh wait, sorry, I'm lying right here. Let me go ahead and restart all this. I want to compare with, I was thinking that was an n on the bottom right there, sorry. 1 over 2 to the n, which is a geometric series that converges. Right, so every time I ever state if something converges or diverges, I say how I know that. Don't just blindly claim anything converges or diverges. So let's put these guys together here and let's do our ratio of the two. So now I'm going to take my limit as n goes to infinity of a sub n over b sub n, and that is going to be the limit as n goes to infinity of root n over 2 to the n, all divided by 1 over 2 to the n. What that's going to leave us here with is the limit as n goes to infinity of just root n, and that's going to diverge off to infinity. So we get no information from the limit comparison test. So, um, notice that sometimes moving from the regular comparison test to the limit comparison test helps, as it did in the first example here, first repeated example. But in the second repeated example, going from our limit to our limit comparison did not actually help us out at all, right? So, and again, we're just looking at all the things that might happen out here. So let's go ahead and let's check out a few more series for convergence or divergence, and then we'll check out section 11.5 and we'll see what's going on with our alternating series out here. So this series 2 over n squared plus 4. One of the things that immediately slightly bothers me about this is that I feel like that 2 is a little bit weird right there, but the good news is that that's just a constant multiple. So I can go ahead and factor that guy out. So this is one tiny thing that I feel like bothers some people sometimes, because that 2 will ultimately make it pretty difficult for you to do things like judge inequalities between two comparison series terms out there. And just by realizing that it's totally acceptable for you to factor out that 2, I think that's really helpful right here. So here's the thing I'm kind of saying. We want to know ultimately whether this series converges or diverges. Since this series right here is just half of it, if this one converges or diverges, then this one converges or diverges similarly, right? They're only off by a factor of 2. Multiplying a number by 2 is never going to push it over the edge to infinity or something like that, right? So basically what that means is we can just answer the question about this series with a 1 in the numerator, because we know it only differs from our original question by a factor of 2. So we can go ahead and compare the series 1 over n squared plus 4 with the series 1 over n squared, which we know converges because it is a p-series with n equal, or with p equals 2 right there. So our comparison here looks like, well, I know that 1 over n squared plus 4 is clearly less than 1 over n squared, since all of our denominators are guaranteed bigger. So I'm going to write this out a little bit differently than I wrote the other ones out here, but I just want to write like my train of thought right here. So 1 over n squared converges by p series, p being equal to 2. I don't know why it just keeps on erasing part of the letters that I'm writing right here. I wish it would just keep them all. And that implies that the series 1 over n squared plus 4 converges. That is by the comparison test. And again, there is no constant multiple you could multiply by that would change whether or not a series converged or diverged. So that multiplication by 2, completely trivial right there. So I, in a sense, removed it from consideration for all the actual thinking that I did. And then I just said, oh yeah, and if you multiplied this is sort of my final answer. The 1 over n squared plus 4 converges by the comparison test. And then, sort of almost as an afterthought, I said, and therefore our original one also converges there. And the reason we can say that is because any constant multiple of a convergent series is going to have to also converge right there. All right, let's see if we can do it again. So this one had an n squared in the denominator, so we jumped on comparing it to n squared. I am thinking over here that this guy right here, this immediately looks to me, and in fact, I'm going to say, since I see that there is that just single factor of n on the bottom down there, I feel like I want to relate this to the harmonic series. But we don't have just 1 over n, we have 1 over 2n. Well, same lesson that we learned from the last one is that I think it's completely reasonable for me to just write this as like 1/2 times the series 1 over n plus 3/2 right there. And now I think that that's not a terrible way at all for me to represent this. I've factored out a factor of 2 that wasn't helping me think about this. It's just distracting me. Now I've just got that one addition subtraction down there, which I'm hoping will be reasonable for me to manage. So let's compare this to 1 over n. And I'm noticing here that 1 over n plus 3/2 versus 1 over n. Well, this one has larger denominators, so this is smaller overall. So ours is smaller than a divergent series. So no info from the comparison test. So what else might we try? Let's try the limit comparison test. We both clearly all have positive terms, so we're good to go for these tests to be used here. It looks like we can represent our a sub n as being the 1 over n plus 3/2, our b sub n as being just our 1 over n, and we can put these together and look and see what happens when we take the limit as n goes to infinity of the ratio of the two terms that we've got right here. And I'm seeing our 1 over n plus 3/2 versus 1 over n is going to lead me to our limit as n goes to infinity of n over n plus 3/2. I am hoping that we can all clearly see that this limit is going to 1. That plus 3/2 is making a trivial difference in the denominator down there. As n tends off towards infinity, our numerator and denominator are clearly eventually going to essentially match right there. And so therefore, by the limit comparison test, the series 1 over n and the series 1 over n plus 3/2 and the series 1 over 2n plus 3, which is really 1/2 times the series 1 over n plus 3/2, all either converge or diverge. And since series 1 over n diverges, the series 1 over 2n plus 3 diverges. All right, so again, we factored out a constant multiple that wasn't going to have an impact on our answer anyway to make doing the math a little bit simpler for ourselves, help make our comparisons a little bit easier. We saw the direct comparison test didn't help because of the fact that was a plus. If that was a minus sign right there, we would have been done just with the comparison test. However, we weren't because we were smaller than a divergent series. We weren't sure if we were smaller enough to converge, and it turns out the answer was no. We're still also going to be divergent down here. Even though we're much, much smaller, we're less than half as big as the harmonic series, but we're still going to diverge according to the limit comparison test right here. Cool. So these are good, and they work hand in hand here, the comparison test and the limit comparison test. If one fails, go straight for the next one right there. It's not necessarily the case that they work both or they fail both. It's often the case that one fails, but the other works. So look at our next one right here. Might as well just bump this one down right here. In fact, can I? Ooh, is it going to get? Yeah, thank you. Wow, that rarely happens so nicely. All right, so let's check out this 1 plus sine of n over 4 to the n. So a little bit weirder here. I want to know if this thing converges or diverges. So less obvious here, right? But again, I see this 4 to the n, and that immediately makes me think geometric stuff here, right? Um, let's say maybe compare with 1 over 4 to the n, which we could really write as 1/4 to the n, which converges. And I know it converges because it is a geometric series with r being less than 1, right? Each term is only 1/4 as big as the term before it right there. And so when we want to make our comparison, we can try to compare 1 plus sine of n over 4 to the n versus, and we want to know, what goes in the box, what's our little comparison term right there, versus 4 to the n. So is this bigger or smaller for all of our positive integers n? And you should realize that the answer is we can't just put down a single greater than or less than right here, because what you know is that sometimes we're going to get positive values for sine, and sometimes we're going to get negative values for sine. So this does not have a consistent greater than or less than relationship with 1 over 4 to the n. No consistent greater than or less than relationship between these two. Okay, so I don't see how this comparison works, right? So let's maybe try the limit comparison then. So I feel like that 1 over 4 to the n is good. We know it converges because it's a geometric series. So I think I can say that my a sub n is the 1 plus sine of n over 4 to the n. And I know that my b sub n is just the 1 over 4 to the n. So the limit comparison test says let's take the limit as n goes to infinity of our a sub n's over our b sub n's and see if they go to a constant or not. This is going to give me 1 plus sine of n over 4 to the n. Keep on dropping my limit statements here. That's not cool. Well, all that's going to give me here is just the limit as n goes to infinity of just 1 plus sine n, which does not exist. It's an oscillating value right there. So no info from the limit comparison test either. So, I mean, the issue with some of these guys ends up being is that when you get stuck, the question is, are you stuck because you made the wrong guesses, or are you stuck because it's actually not possible to prove that type of information here, right? So here's the thing that I'm thinking. This sine of n is screwing with me right here. It's really my problem in our direct comparison. It's really my problem in our limit comparison right here. But I feel like sine of n just shouldn't be that big of an issue when we're dealing with these because we're only varying by small amounts up there in that numerator. The denominator is getting massive immediately. The numerator is hanging out around really small values. So I'm thinking to myself, maybe there's a different thing that we can compare to that's based on what we already know about this whole sine function that exists out there, right? So I feel like we need a new comparison. And here's what I'm thinking. I know that negative 1 is less than or equal to sine of n is less than or equal to 1. And what we've got up in the numerator is 1 plus sine of n. So I'm just going to add 1 to all three components of my inequality here. And what I can see here is that I know that 1 plus sine of n is guaranteed to be less than or equal to 2. So maybe let's choose the series 2 over 4 to the n as our comparison series. The series still converges. It's 2 times a convergent series. All right, this is just taking double of the series 1 over 4 to the n, which we know to converge. Converges to 4/3, so this is going to converge to 8/3 right here. Um, so this should be a perfectly reasonable comparison partner for us now. So now I think I can make the statement that says 1 plus sine of n over 4 to the n. This is definitely less than or equal to 2 over 4 to the n. This is true for all n greater than or equal to 1, all the n's that we're actually going to consider. And so it looks like we actually just needed to make a smarter comparison. By the comparison test, the series 1 plus sine of n over 4 to the n converges because it is less than the convergent series 2 over 4 to the n. Okay, and so I wanted to amend what I was writing right there. The reason I just made that little scratch out edit right there is because we're really not comparing the value of the series to the value of the comparison series. We're considering the individual value of one term to the individual value of its partner term at the same index of the series right there. So individually, we're making a term by term comparison. We're not making an overall comparison from one series to the next. We're making a term by term comparison, and that's kind of the important little technical distinction that I wanted to make right there. So it seems like we were able to show this series does converge, and a pretty typical thing to do whenever you see your trig terms crop up is to do some little inequality maneuvers like this to find what is the constant that is perhaps an upper or lower bound on a expression involving trig terms there. It makes it so that you don't have to think about the fact that trig functions oscillate. 2 doesn't oscillate, right? And so it sort of removes that oscillatory component, which was our issue in the previous 2 attempts. The reason we couldn't make this comparison is because sine was sometimes positive, sometimes negative. The reason that we couldn't use the limit comparison test is because this limit right here was a divergent limit because it oscillates. And so we got rid of the oscillating component by forming this compound inequality right here that allowed us to proceed on with just the regular old comparison test right there. All right, pretty nice. Okay, so that I think is our last, yeah, that was our last example right there for 11.4 with the comparison test. Now I want to go ahead and hit up section 11.5, alternating series. So this video is going to be a little bit longer than average, but still the two sections collectively are not too terrible. We're going to get a really good theorem for our alternating series right here. We're going to see that we can apply it with just as much ease as we just did our comparison tests right there. So let's go on ahead here with our alternating series. So in section 11.5, alternating series. By definition, an alternating series is a series that alternates between positive and negative terms. Since it alternates between positive and negative terms, it is always possible. If you are an alternating series, then you can be written of this form. You should notice that this negative 1 to the n power is always going to handle our positive negative sign changes. Therefore, this b to the n is always a positive term. The positives and negatives are going to get handled by the alternating factor that's in there, that negative 1 to the n power. Remember that since n is always going to be an integer, that's always negative 1 to an integer power, which means we're just alternating back and forth between positives and negatives as we go even, odd. So our essential convergence and divergence test is associated with the with alternating series is very similar to the monotonic sequence theorem that we saw back in section 11.1. So let's go ahead and take a look. Back in section 11.1, we kind of arrived at the monotonic sequence theorem, which said if you have a sequence, what's wrong with me? Sequence defined as a sub n, where all the terms are a1 through an, right? Or not through an, defined as an. then if that series was monotonic and bounded, then the series is going to be guaranteed to converge, right? That was our first convergence theorem that we got in this chapter. Today, we're going to get now the alternating series test, or the AST, that I'll abbreviate many times in our upcoming examples. And that says, given that we have a series that is of this form right here, and you should notice one tiny distinction is that I stated it up here as negative 1 to the n. This states as negative 1 to the n plus 1. I think the reason it does that is just to suggest that this always starts with a positive term right here. Notice that if n equals 1 is the first index that we use, then 1 plus 1 is 2. Negative 1 squared is positive, so that gives us always a positive term first right there. Given a series of this form, where then it looks like b1 minus b2 plus b3 minus b4, remember, and this is an important one for us here today, that this b sub n, the sequence associated with b sub n, is all positive numbers. Any negatives are always going to be handled by the alternating component that sits out front right there. Then if it is the case that the b sub n's, meaning only the magnitude, ignoring any sign changes, the sign changes are not in the b's, right? If the magnitude of those b terms is always decreasing, right? If the next term is smaller than the current term, if it's always guaranteed to be decreasing or at least non-increasing, because we get the or equal to for all the n's, and if the sequence of b terms tends to 0, then this is going to be a convergent series. So, oh my gosh, what's wrong with me up here? Here's the way that I like to think about why this one is true right here. Why do I like to think about this one? Why is this true? So here's what I'm thinking. What I'm thinking is every time these b terms are their magnitude, right, in absolute value is getting smaller and smaller and smaller. So we're starting with some number b1. It's I'll call it a large, very much in quotation marks. It's larger than every other term, right? b1 is larger in magnitude than every other term in the infinite series. We're starting at b1, and we're going to chop it down by a little bit, b2. But then we're going to increase it a little bit by b3. Then we're going to decrease it a little bit by b4. So what I'm kind of seeing for myself here is that we're going to start out here at b1. You know, there's my b1 value. But then it should be the case that we are kind of flopping back and forth, back and forth, back and forth, adding to it, subtracting to it, back and forth over and over and over again. And you should notice that kind of what this is going to mean is that since b1 is the largest term in the series, since it's guaranteed that we're going to chop off the next biggest term in the series, but then re-add the next biggest term in the series, what's going to happen is that this entire series then should be bounded above by b1, because it's guaranteed to be always monotonic, or sorry, always decreasing or constant. And as long as the contribution eventually goes to 0 of the adjustment that we're making to b1, which I consider every other term to be the adjustment that we're making, then it should be that it's sort of like saying eventually you stop adjusting and this bouncing back and forth is just converging on a known value. So the thing to see here is that this, because of this always decreasing and because the contribution is always tending down to 0, this is always bounded above by b1. It's always bounded below by 0. And the change is eventually going to 0, meaning it's not just sitting there bouncing back and forth, negative 1, positive 1, negative 1, positive 1, negative 1, positive 1, or anything stupid like that, which would be diverging. It is guaranteed to be honing in on something because the eventual contribution to the adjustment of the current sum so far is eventually 0. So that's why I feel like this is very, very, very similar to the monotonic sequence theorem right here. It's sort of doing a similar flavor thing. It's just doing some bouncing back and forth rather than like a gradual progression right there. So let's go ahead and test some series for convergence and for divergence. So the very first example right here you can see is exactly in the structured form that we want it to be in to use the alternating series test. It's literally written in this form. We've got the negative 1 to the n power right there. So I think we can go ahead and use that alternating series test right there. So remember, this is our b sub n right here. This is actually the magnitude of all the terms, b sub n, not b to the n power right there. And so this is really the thing that we're going to be like managing right there, right? So this is, let's just say, this is in the format associated with the AST, alternating series test. So let's see if it meets the two requirements. So what you're going to see in this section is a little bit tougher algebra. We're going to have to actually do some math to convince ourselves that these statements are true. Remember that the two statements that we need to show is that these b sub n terms, and again, we're just completely ignoring all the positive negative component when we talk about b sub n. We're talking only positive values, magnitudes, right? We need to show that this is always a decreasing sequence, this b sub n, and we need to show that the limit as n goes to infinity of the b sub n equals 0. So if we can show these two things, then it's convergent right there, all right? So let's see if we can show those two things, right? So one, I need to show that the sequence is non-increasing, right? B sub n plus 1 is less than or equal to B sub n right there. So how am I going to do this? So this seems to be suggesting to me that I want to show that 2 times n plus 1 over 4 times n plus 1 squared plus 1 is less than or equal to 2n over 4n squared plus 1. I'm going to go ahead and say I don't really feel like just doing a mountain of quadratic algebra right there to see if I can arrive at some legit statement right there. Here is the thing that I'm thinking instead. Instead, let's think about how fractions work. How could I show you that a number in terms of n as a fraction is guaranteed to be decreasing? Well, what would need to happen is that, and notice also, here's another important feature of this. Every time n gets bigger, both the numerator gets bigger and the denominator gets bigger. So it seems like what I need to be able to show is that the denominator grows at a faster rate than the numerator grows to show that it's decreasing here. So it looks like from a couple quick derivatives, for all values of n. I can see that from my quick derivatives. So it looks like we're going to be able to confirm that b sub n plus 1 is in fact less than or equal to b sub n based on that guy right there. All right. So I think that by doing actually a little calculus, I have shown that this is going to be a decreasing sequence right here. The other thing that we want to do is we want to show that the limit as n goes to infinity of b sub n equals 0. Limit as n goes to infinity of 2n over 4n squared plus 1. I am hopeful that you guys are all in total agreement that this does, in fact, tend to 0 right here. This is, and I'll just write it out, I guess, but this is that one where if we really want to show our math officially, we can factor out that term of n and write this as 2 over 4n plus 1 over 0. Oh no, I guess we need to factor out an n squared, right? And then we get the 2 over n is the numerator, 4 plus 1 over n squared, and then we get this to be a 0 over 4 plus 0 equals 0. So it looks like this limit did in fact converge to 0. So by the AST, the series negative 1 to the n times 2n over 4n squared plus 1 converges. All right, we showed that we met the two requirements. We saw that we fit the structure associated with alternating series. We then used the alternating series test to show that it was a decreasing series. It was a series where the terms eventually converge to zero, and therefore it must be a convergent series overall. Now, let's look at our next series here, which is a little bit grosser. That last one at least involved a rational function. Now we've got exponentials with fractional powers. It's kind of ridiculous right here. Again, I want to remind you that we're thinking of this guy as like our b sub n right here, and I keep on writing b to the power of n, and it is in fact b sub n. And so let's go ahead and attempt to show, so let's say to use the AST, need to show b sub n plus 1 is less than or equal to b sub n, and that the limit as b sub n, or that limit as n goes to infinity of b sub n is equal to 0. Oh my gosh, oh my gosh. Right, okay, I have to say it out loud. Limit as n goes to infinity of b sub n equals 0. All right, so those are the two things we need to show. Let's see here. Neither of these seem to be 100% obvious to me. I guess the limit looks reasonable. So I'm going to do the limit first. So I'm going to label that number 2. I'm going to show it the limit as n. I really just want to stop writing this limit statement since I can't write it. N goes to infinity of b sub n. I almost just wrote that wrong like 4 more times still. It's crazy. So what are we trying to do here? Limit as n goes to infinity of e to the 1 over n over n. Now what I'm thinking here is as n gets infinitely large, 1 over n gets infinitely small, right? This is converging to 0. So it looks like what we're getting here is e to the 0 over, I guess I should have, let me do this here, over infinity, right? Which is really just like 1 over infinity, which seems like we're heading off towards 0 right there, right? So it seems like that numerator up there as n gets infinitely large is tending to the number 1. The denominator is just getting infinitely large. So we're getting 1 over an infinitely large number, which is going to tend us towards 0. So I feel good that our individual terms b sub n are converging to 0. So I've shown one of the two things I need to show. Now, the thing that seems less obvious to me is I want to show that the sequence is decreasing, right? That our every next term is smaller than or equal to the current term. So what does that look like for me here? Well, that should be e to the 1 over n plus 1 over n plus 1 is less than or equal to b sub n, which is just e to the 1 over n over n. And I don't know what to do to directly do this right here. My issue is it's really difficult for me to compare exponentials with with linear terms, right, with polynomials. So maybe what I'm thinking to myself is this. Maybe let's group up all the polynomials on one side and all the exponentials on the other side and see if we can kind of revisit this to make a statement. So I'm going to just do some cross multiplying. I'm going to multiply n plus 1 to be up in this numerator, and I'm going to divide the e to the 1 over n to be in this denominator right here. Right? Does this help me at all? Well, the reason why this is good is because, like I said, it's easier for me to make those direct comparisons now. For example, this expression over here, n plus 1 over n, it's very easy for me to see that this is always bigger than 1. Because we've got a larger numerator than we've got denominator out there, right? That fraction is always going to be bigger than 1 for all n. Now, what do I got going on over here? It looks like we're taking a root of e, right? So we're taking roots of a number that's larger than 1. It looks like up here we're taking large roots of e, like a sixth root of e, whereas down here we're only taking like a fifth root of e. I know that when you take roots of a number that's larger than 1, it always decreases the number. And up here, we're taking more roots. So it seems to me like this numerator has to always be smaller than this denominator, meaning this is always less than 1. So I think that by that comparison right there, if this term is always less than 1 and this term is always bigger than 1, then that guarantees that they're going to have that less than relationship. Uh, So I think that gets us a check mark there as well, right? So again, our goal was to show that that less than or equal to was legit. I showed that the value that was smaller was always less than 1, and that the value that was bigger was always bigger than 1. So it seems like it's acceptable for us to say 1 over n plus 1 over e to the 1 over n is less than 1 is less than n plus 1 over n. We just showed that that statement is true and that that statement is true. Therefore, this is less than this. Therefore, b sub n plus 1 is less than or equal to b sub n. So we are decreasing. And therefore, so we can conclude by the AST converges. Right? Not obvious at all how we're going to do the math for either of these guys right here. So recognize again, this is kind of like back when we introduced that proof by induction. It's not just going to be screamingly obvious to you that any of these individual features, these hypotheses for these tests and theorems are going to be true. So a lot of what your work is figuring out proper ways to show your limits, proper ways to show your inequality relationships between two things here. Ultimately, a lot of this amounts to algebraic manipulation and kind of cleverly setting up some inequalities, but like they're not obvious for sure, and that's why it's kind of interesting that these proofs are in a sense they're a little bit more artistic than other things in that you have to be creative. I'm sure that there's 20 different ways to show these types of statements that are out here. Got to be creative with these things here. So let's go on to our next example here. So you should notice that our next example is not written in series form right here. So my first mission might be to say, what series even is this right here? Now, the one thing I am seeing is it does look like this is an alternating series. I see the negative, positive, negative, positive, negative right there. So this looks like an alternating series. But my alternating series test is only dependent on me knowing b sub n. So I want to say it looks alternating. But need it in negative 1 to the n b sub n form to use the AST. Right? So basically that says if we can't come up with what the sort of the function version of this looks like, then we kind of can't do it. So here's the thing I'm seeing. I am seeing that we're getting all a linear transition on top. We're just adding 1 every time. So that looks like that's just literally n. N is 1, n is 2, n is 3, n is 4, n is 5. On bottom, we're also getting an increase by 1, but we just start a little bit later down there. So it seems to me that this is going to be the series here that starting at 1, and I'll indicate it on this one, starting at 1, it looks like this is negative 1 just to the n, because notice n being 1 says our first term should be negative, which is exactly what we have right there, times what is our b sub n function right here? Well, it looks like our first term had 1, second term had 2, third term had 3 up in the numerator. So that literally is just what n is going to be. And it looks like the other thing I'm seeing is that the denominator is always 2 larger than the numerator. So I think n plus 2 is what's going to go there, right? So the thing that I'm seeing here is that if I were going to use the alternating series test right here, we'd need to, show our two hypotheses. oh my gosh, if I write this limit, I just can't write it. I'm gonna write a b down there literally every single time. I can't help it. So question one is this what's happening? All right, do we satisfy these two hypotheses? Are these are these values getting smaller? And here's the thing I'm immediately seeing: 2/4, which is 1/2, is the second term. 4/6, which is 2/3, is the fourth term. This doesn't appear to be decreasing at all. In fact, it looks like this is an increasing sequence right here. Let me give this a big old note. And notice that n equals, pick any of them. N equals 2, b equals 1/2, n equals 3, b equals, and I'm going to say this is a decimal, 0.5. At 3, we're getting 3/5, which is 0.6. It's not decreasing. So, based on this alone, we have failed the alternating series test right here. Right? You should notice also over here that this limit is also not going to work out. Right? So it looks like both hypotheses of the alternating series test have failed. So that means the alternating series test gives no information. So can we say what's really happening here? Well, what do the terms of this sequence eventually look like, or this series? So what do they eventually look like? Well, plug in n equals a billion. What are you going to get? When n equals 1 billion, I'm going to get an even power, so I have a positive number. 1 billion divided by 1 billion and 2 is about, it's about 1, right? Then I plug in a billion and 1. I'm going to get a negative number, and I'm going to get about 1 from this ratio, right? So it seems like eventually what this series seems like it's doing is just dinging back and forth between +1 and -1. We are wondering if the value of this series is ever going to converge. And if you recall, let's see here, in 11.2, the divergence test said that if the terms of a series do not converge to a number, the series diverges. So, by the divergence test, the series -1 to the n times n over n plus 2 diverges. All right, so a bit of a weirder one right there. And again, the important thing about this one was that we weren't given it in like written in series notation. So our first step was that we needed to write it that way because it clearly looked like an alternating series. That clearly leads me to think alternating series test. Alternating series test depends on us knowing our b sub n. So we had to get it in that form. We saw that we failed both of the hypotheses associated with the alternating series test. And all we had to do was fail one, and we were going to get no information from it there, right? So instead, we stopped and broadly thought a little bit more about this. And I think that this is one of those series where it seems easier to think about what it seems like in this form than it does in this form, which is why this is always a practical thing to write it out in our series notation form right there. I think it's relatively easy to see that this eventually just becomes bouncing back and forth between 1 and -1. And this is something that we already discussed in 11.2, that our divergence test said if the terms in your series don't eventually condense down to, or don't converge on some number, it doesn't even have to be zero, it just has to converge on some number. That's a non-diverging sequence right there, of terms within our series, then it's not going to converge, it's going to diverge. So according to the divergence test, this diverged right there. All right. So what about another one that's in this, summation form right here, as opposed to being in our in our series written form right here? So let's go ahead and take a look at this one, and then we'll see one more example here with some more trig things that are going to screw with this, and we'll go ahead and call it a day here. So looking at this next example here, I can see that immediately that some of our issues are fixed, right? Um, Seems alternating. Let's get it in -1 to the n b sub n form. So what do we see? It seems to me like the first term is going to be a positive term right here. So it seems like this should be the series from n equals 1 to infinity. If I do -1 to the n, then by plugging in 1, I'm going to get a negative. But my first term is positive, so I'm going to make that an n plus 1. What do my b sub n's look like? Well, it looks pretty obvious what my numerator is for every single term. My denominator grows linearly starting at 7, right? So it seems like down here, I'm thinking to myself, my first term gives me 7, second gives me 8, third gives me 9, fourth gives me 10. Seems like there should just be an n plus 6 down there on the bottom, right? Remember that n is starting at 1, not at 0 right there. So if n is 1, you get 7 on the bottom down there for that very first term. So it seems like I can write it in this form, and so this is good because now I've got my b sub n right here. So now can we show the two hypotheses? The two requirements of the AST. And let's see, the first thing that we want to show is that it is a decreasing series, or decreasing sequence. The terms in the series are decreasing. That would be 4 over what? N 4 over n plus 1, which is really n plus 7 then. So less or equal to 4 over n plus 6. Clearly true for all positive n's. That's good. And can we see at the limit as b sub n? Oh my gosh. Are you kidding me with these freaking limits down here? Let me write one like a normal person. Hopefully you can also see that this one very clearly is going to 0 right there. The only n is in the denominator right there, as that gets really big right there. So that gets the check mark. So I think we can say by the AST, the series -1 to the n plus 1 times 4 over n plus 6 converges. All right, that one was not that bad right there. The only effort that was involved was getting that into its series notation rather than being explicitly written out there. Right? So let's go ahead and look at one last example for the day, and this will wrap up our alternating series. I do want to point out real quick, just before we conclude with our final example here today, that we're wrapping up 11.5 right now. Section 11.6 that we're going to hit in the next video covers absolute convergence. That is referring to absolute value that is associated with negative terms being in there. So right now what we're talking about is a series where we perfectly alternate every single term, positive, negative. The absolute convergence idea is going to include some absolute values in some of our statements, but it's going to help us talk about what happens when it's maybe like 2 positive, 2 negative, 3 positive, 4 negative, something like that, where it's not alternating sign, but does change sign. So we're still going to talk about more of these positives versus negatives, dealing with these negatives with those -1 to the power ofs and stuff like that in the next video. That'll certainly be a component of that. So this isn't going away. We're just doing sort of the easy ones of the positive and negative termed series today. So what's up with this guy right here? The sine of n pi over 2 over n factorial. I think that the first thing that's kind of obvious to me about this series is that it doesn't necessarily seem like it's necessarily alternating. It's not clear that this is alternating. We want this in the form -1 to the n times a b sub n. So my question is, if this is alternating, it can be written in that form. So let's take a look at some terms and see what this looks like. Let's see what we get here. So if I plug in 1 into this thing, I'm going to get the sine of pi halves. Sine of pi halves is measuring vertical height on the unit circle, so we'll get 1, and that's 1 over 1 factorial. And by the way, one thing I'm going to say to you guys is, whenever you see factorials in things, I would highly encourage you to not multiply them out and leave them in factorial form unless you have a really good reason to multiply them out. Otherwise, it just gives you tons of numbers that you can't manage. Leave factorials in factorial form to be nice to yourself. Next, I'm going to look at n equals 2. 2 pi over 2 is just the sine of pi. So sine of pi's height has 0 right there. So we're going to get a 0 over 2 factorial. When I plug in 3, it seems like we're going to get 3 pi halves, which is pointing straight down. That's going to give me a sine of 3 pi halves is -1 over 3 factorial. 4 pi halves is 2 pi, so that's going to give me a 0 on top over 4 factorial. 5 pi halves is going to give me a 1 on top over the 5 factorial. 6 pi halves is 3 pi, so it's a 0 on top over 6 factorial. And I think I should write one more for the alternatingness of it. 7 pi halves is back around right here to where we were at 3 pi halves. That's going to give us a, or excuse me, 7 pi halves is 1, 2, 3, 4, 5, 6, 7. 7 pi halves is straight down. So that's getting us -1 out of the sine function right there over 7 factorial. So it seems to me like I can kind of see the structure of this thing right now. It seems to me like what we're really going to be getting right here. So let me write this out a little bit more. So the series sum of sine of n pi over 2 over n factorial. What are we getting? We're getting 1 over 1 factorial minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial dot dot dot. What I want to know now is, now that we see it in this way, what's our better way to write this series right here? God, sometimes I write the dumbest looking sum signs right there. It drives me nuts. What are we getting right here? How's this going to work out for us? Well, one thing I know I need is a -1 to some power. So let's do that part first. I need -1. It looks like our first term is positive here. So it seems to me like I want this to be an n plus 1, so that when we plug in n equals 1 for our first term, we get -1 to an even power. So I think that's going to handle our positives, negatives. Now I'm saying, what's up with the actual magnitudes of each of these numbers? Well, I can see that they're all fractions. They all have a 1 in the numerator. And they all have some terms of factorial in the denominator. But what I'm seeing here is it's really just all odds is what we're getting. In general, if you're thinking about odd numbers, when we're plugging in all integers, you can get an odd integer by doubling your integer and adding 1 always here. So to double it guarantees that it's even. To add 1 then guarantees that it's odd. So 2n plus 1 and 2n minus 1 are very typical representations of odd numbers. Let me just say this over here. Evens are typically denoted with 2 times n, because that says take in any integer n and double it, you're guaranteed to get all the evens. Odds, on the other hand, are typically denoted as either 2n plus 1 or 2n minus 1, because to go to 2 times n for any number makes it even. From an even number, you either got to go up 1 or down 1 to get to your next odd. So which one should it be? 2n plus 1 or 2n minus 1 for these odds here? If I do 2n plus 1, then when I plug in n equals 1, I'll get 3, but that's not what I want. If I do 2n minus 1, I'm going to get 2 minus 1 is 1 for the first. 2 times 2 is 4, minus 1 gives me 3 for the second. 2 times 3 for my third term gives me 6, minus 1 is 5 for the next. So it does seem appropriate here that a 2n minus 1 factorial seems to be my denominator term that I'm getting down there. Again, these are pretty common things. Anytime you identify evens or odds, this is like almost always a good way for you to go about describing a general even number or a general odd number right there. So we've got our expression right here. It looks like this is now the b sub n of interest to us for using the alternating series test, which I think I can do because we're now clearly in alternating series form. Okay, so what do we got to show here? One, we got to show that this is a decreasing series. Two, we've got to show that the size of the b sub n's goes to 0. So let's do those two things. So first, we want to show that b sub n plus 1 is less than or equal to b sub n. Looks like in this case right here, I am getting 1 over, I don't need that outside parentheses right here. I've got 1 over 2 n plus 1 minus 1 factorial is less than or equal to 1 over 2n minus 1 factorial. It looks like this is really, so do the mental math with me here. This is going to be a 2n plus 2 minus 1. So that's really a 1 over 2n plus 1 factorial is less than or equal to 1 over 2n minus 1 factorial. This obviously has the larger denominator, and so therefore this is obviously the smaller of the two fractions right there. So I'm just going to give that guy the check mark right there. For our second requirement associated with the alternating series test, we want to show that the limit as n, this is my last chance to get this right, n goes to infinity of b sub n, needs to be equal to 0, right? So let's see that our limit as n goes to infinity of 1 over 2n minus 1 factorial. Well, I'm hoping you guys are down with the fact that this is clearly tending towards infinity in the denominator down there. Factorials grow insanely fast. That is an outrageously rapidly growing function that's down there in the denominator. It is definitely the case that this is tending towards our 1 over infinity, which is going to take us to 0 right there. So it does look like by the alternating series test, the series sine of, what was it, pi n over 2 and pi over 2 over n factorial, which is equal to the series. Ooh, now I want to make one tiny distinction right here. I wanted to say, all right, here's my last thing for the day right here. What I wanted to say was that these are equal to each other, but you should notice that this works out when I plug in like n equals 2 here, I get a 0. When I plug in n equals 2 here, I don't get a 0. So I should have changed letterings away from n. These two series do represent the same thing, but not at the same index locations. Again, half of all of the terms in this series are 0. If you just drop them all, you get all the terms that are in this series. So this sum is equal to this sum, but it's not true that these individual, like if you say, what's the seventh term of this series? It's not the same as the seventh term of this series over here. So I should have switched variables that's associated with that guy right there. So maybe what I'll do right here is just say that this should be like the sine of negative 1 to the k plus 1 of 1 over 2k minus 1 factorial right there converges. And I'm going to write out that comment right here. But otherwise, that's going to conclude it for me. So I'm going to write this comment. I don't need you guys to see me write this. It's going to wrap it up for our 11.5 video right now. We're going to hit 2 more sections again. It's going to be a video a lot like this one here today to talk about absolute convergence, the ratio test, and the root test, which are almost identical to one another. And in general, 11.7 is strategies for testing series. So all that really means is I'm just also going to do a bunch more examples in that section so that we can see like all the things that happen. We're going to see some scenarios where we're really going to run down our checklist and say, can we try this? 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 And we're going to see that we're finally going to get a proof of convergence or divergence on like our 6th test or something like that. So we'll see some of those good 11.7 examples kind of littered into our 11.6 topic right there. And that will kind of conclude our series testing after the next video there. So I will see you guys for 11.6 and 11.7 in the next video. Have a good one.